Welcome back to another session of Physical Sciences. We will again today look at chemistry. We will specifically look at chemical equilibrium. Now, at school you were supposed to do by now the rates of chemical reactions for you to have a better understanding of chemical equilibrium. Just before we start, I would like you to think of the following question. What does the word equilibrium means to you? I would like you to think about that while we're going through the chemical equilibrium and while we're talking about the reactions and the definitions for the next few sessions. If we look at the concept map of chemical equilibrium, I would like us to go and start off by trying to get to the definition of chemical equilibrium. Now, before we can get to the definition of chemical equilibrium, there's a few other things that we need to look at. And just before we get there, I would like us to go look at the terminology that I will use during the chemical equilibrium lesson. We will look at words like open system, closed system, and reversible reactions. So let's start off. Firstly, if you look at an open system, is a system where the reactants or the products can escape. In other words, it is a system where you might start with a solid and an aqueous solution or with a gas, but at the end of the day, for an open system, that reactants, when forming a product, can then escape, meaning it might then be in gas form. It's continually acting or interacting with the environment, and the conditions are not kept constant, because should you change anything to the environment, it might have an effect on the open system. For that reason, we can say an open system, being in contact with the environment all the time, will then have variables that's not kept constant during the experiment. If we look at an example, if this is a beaker where we have, or a reaction vessel where we have our chemicals in, we can see that this is open and it is physically open as well. So there is some interaction with the surroundings. This is the surrounding anywhere around that vessel, and the reaction at some stage for an open system will finish. Why will it finish? The reaction will finish because one or both of the reactants will get used up. Because in an open system, your reactants form the product and no more new reactants are made. So if you start with a certain amount of reactant, it will form product. And as the time goes on, the reactant, one or two of them will get used up, and it will end up stopping or finishing at a stage. Next, I would like us to look at closed system. Now, closed can mean something where we have reactants that does not form a gas, meaning the reactants is also not in a gaseous phase. Then we can have a closed system. But just remember, we can also have a closed system as a system that is physically closed, meaning that the vessel is closed to make sure there's no contact with the surroundings. A closed system is where your reactants or your products cannot escape. Even if there's a gas that's forming, it's said to be an isolated system because it's not in contact or interacting with the surrounding. And because it's not interacting with the surrounding, it basically means that your variables remain constant during the experiment. If we have an example of a closed system here, it's physically closed where we have our reactant vessel and we have a bell jar that's closing it. You can see that there's a reaction happening and the reaction comes back into the vessel, meaning there is some sort of reverse happening because none of the product or the reactants can go out of the system. That means that there's no interaction with the surroundings. Everything that happens in this closed system, and this reaction will not finish. Why will this reaction not finish? It will not finish because as the reactant form product, the product become more and more, and at a point where there's enough product, that product might start to form some of the reactant again. So if you can see here, we use 2 arrows to show that we have a reaction and that reaction can return. It is not in contact with the surroundings, and we then say this is a closed system. First, before we get to reversible reactions, let's first talk about irreversible. Now, irreversible means it's a reaction that cannot be reversed. Now, what comes to mind for me when I think about an irreversible reaction is when we brine meat, when we have a barbecue. Remember, you start with raw meat with some spices on the meat, and as you do your barbecue, there's a lot of fat splashing all over the place into the coals, and as you turn it around. Can that meat be taken back to raw? No, obviously not. Where will you find all the splashed fat and the spices and everything? So when you brine meat, the meat will never return to be raw again. The same when baking a cake. Think in terms of having flour and oil and eggs, and you mix all of these with milk. You have a little dough, and you put that into a baking tray to bake a lovely chocolate cake. Now, my question is, when that chocolate cake comes out of the oven, it's a new substance. It's a new product because all the reactants has now formed into the product. Can we take that cake back to the flour and the eggs and the milk and the oil? No. Because we cannot reverse the reaction, we call it an irreversible reaction. And that brings us to reversible reaction. I want you to see that there is a double arrow that we use to basically show that a reaction is reversible. A reversible reaction occurs when the products can convert back into reactants. So you have your reactants that convert into product, and then at a stage the product will convert back into reactants. This can only happen when you have a closed system. And remember, we use the double arrows. The double arrows meaning there is a reaction where the reactants convert into product, and simultaneously or at the same time, the product now convert back into the reactant. We call that a reversible reaction. And that brings us to the point where we see the concept map again. Yes, let's take a break. See you soon. Welcome back. I hope we are all refreshed. I certainly am. And I hope you are ready to go on with chemical equilibrium. In the first session, we worked up to a point where we looked at the definition of chemical equilibrium. What we're going to do now is we're going to build on that definition of chemical equilibrium, and we will start to show some graphs with that chemical equilibrium so that we can start to understand and to see while a system is building up to equilibrium, the rates that we will look at, as well as at the end we will look at the concentration. How does the concentration change as we build up to chemical equilibrium? In front of us is an example of a reversible reaction. Remember what we said, what is a reversible reaction? a reaction where the reactants convert into product, and when there is enough product, the product will convert into reactant, but that process happens at the same time. We actually use the word simultaneously. So when we look at the production of ammonia by using nitrogen and hydrogen, in front of us we have a balanced reaction. It is very important that the reaction is balanced. Now, if we break up this reversible reaction into firstly the forward and secondly the reverse reaction, we firstly can say the reaction that we read from left to right is the forward reaction. So the forward reaction, if we only write down the forward reaction, we will not be using the double arrow. We will only use an arrow pointing in the direction of the formation of the product. So back to hydrogen and nitrogen reacting to form ammonia. That is read from left to right, and our arrow will be to the right. When we write the reverse reaction of what happens here, we can write it the same, but we need to remember that it will now change. We change the arrow to the opposite side. Why? Because when we look at the reversible reaction, what was the product now becomes the reactant. And that reactant will now decompose in this case to form what was the reactant to be the product. I think I confused you now. Let me say the following. This is now for my reverse reaction, which is actually read from right to left. This is now my reactant. And my reactant is now, I show with my arrow, breaking up into the product of the reactants. On the forward reaction, these were the reactants. And this was my product of the reactants. Okay, just another note, that reverse reaction can also be written starting with our ammonia. So we can actually also write it as 2NH3, but what's now going to be very important is that we have an arrow showing forward, and we then show this is our products that's forming. So we must remember that the arrow must change when we write it in the opposite way. When we look at the forward reaction of this reverse reaction, make sure that you focus on the arrow there. You need to know that at the beginning, we have a high concentration of hydrogen gas and we have a high concentration of nitrogen gas. And the high concentration is due to the fact that it's the only thing that's currently in the vessel. So we have lots of nitrogen and lots of hydrogen. And because we have lots of hydrogen and lots of nitrogen, the reaction will actually be very fast. What about the ammonia? In the beginning, there is no ammonia, therefore there will be no reaction. Not just reaction, there will be no reverse reaction in the beginning. If I can go to a graph and plot a rate over time graph, I can actually do the following. Remember, we started off with a high concentration of nitrogen and hydrogen. So for the forward reaction, we had loads of this, and because we had loads of it, we had a high rate of reaction because there were lots of particles that could collide. And remember what we said, more collisions there is per unit time, the higher the likelihood of effective collisions, and that leads to a high rate of reaction. When we look at the reverse reaction, where the nitrogen where the ammonia now convert back into nitrogen and hydrogen, remember at the beginning there is no reaction reverse, therefore we make our plot on the 0. After a while, now the reaction started. Remember at first we had loads of nitrogen, loads of hydrogen, very fast reaction. There was no ammonia at the beginning. So we plotted the 2 points. Now, after a while, we will see that the hydrogen and the nitrogen concentration start to slightly decrease. And that happens because now the ammonia started to slightly increase. And when this slightly decreases, it starts to slow down. The reaction starts to slow down for the forward reaction. And while the reverse reaction is now getting more ammonia in the system, the reverse reaction starts to slightly increase. And this slight increase and slight decrease can be shown on the graph. Back at the graph, this was at the beginning, and this is now after a while. You can see that my forward reaction actually starts to slow down. And in that process, I have my reverse reaction where the concentration of the product, which is NH3, is now starting to increase, and the rate is also starting to increase. So we have more or less 2 plotting points after a while that will look like that on a rate time graph. Even a little bit later, remember we still have nitrogen, we still have hydrogen, but we also have ammonia now in the system. But the nitrogen and the nitrogen has become less and less over time, so it still decreases, but not at a high rate as before. So it decreases, but to a lesser extent. The ammonia still increases, but not like before. It also increases less per unit time. So even though this reaction starts to increase the rate, it's not as fast as before. So the forward reaction now actually slows down because of this decrease. And the reverse reaction increases slowly because of the increase of my ammonia concentration. That brings us to the graph. Now I want you to see what we've done on the graph now. I've now plotted the points over time. So I'm just going to explain again. What happened to the rate here is at the beginning we had loads of nitrogen and hydrogen that started to convert fast into our ammonia. At the beginning for the reverse reaction, there was no ammonia, but as soon as it started to convert and make ammonia, we had a reaction that looked like that. So if we would complete this, our rate of reaction graph will look more or less like that, and that is now for the overall reaction, where we look at the forward reaction and the reverse reaction. Then at the end, finally, our hydrogen and our nitrogen stops decreasing. Our ammonia stops increasing. So what happened here is for both the forward and the reverse reaction, the concentrations of everything became or becomes constant. Not the same, the word is constant. So when we look at the overall reaction of the rate of the forward reaction and the rate of the reverse reaction, we can actually put it into a graph where the orange part will be our forward reaction and the reverse reaction is the blue graph, where we can see at this point from here onward, we actually have the rate of the forward reaction is equal to the rate of the reverse reaction. And that brings us to the next point, and that brings us to the actual definition of chemical equilibrium. Now, chemical equilibrium is a type of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. It must happen in a reversible reaction, and it will only happen in a closed system. So the rate of the forward reaction must be equal to the rate of the reverse reaction. A closed system, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. Concentration of reactants and products that remain constant, these are all features of a chemical equilibrium. So if there's no closed system, there will not be a rate of a forward reaction that can become equal to the reverse reaction. So please make sure that you realize that chemical equilibrium can only happen in a closed system where the two reactions are at the same rate and the concentrations remain the same, constant. When we look at the concentration time graph for the same reaction, I want you to remember that I'm now looking at concentration. So the purple pink part will represent what happens to nitrogen over time. The yellow is what happens to hydrogen over time, and the red, the ammonia. So the concentration shows us that we start with high concentrations of nitrogen and hydrogen, and they will decrease over time in concentration, but we start with no concentration for ammonia at the beginning, and that will increase over time. Please make sure that you look at, when you get a graph, you must make sure, is it a rate graph or is it a concentration graph? Okay. Then at the point where we have horizontal lines, or let's say this horizontal lines are now parallel to the time axis, at this point all the concentrations of the reactants and the products remain constant. Remember, the word is constant. We do not say the concentrations are the same. Dynamic equilibrium. Remember when I gave you the definition of chemical equilibrium? I said it is one of the types of dynamic equilibrium. Now, dynamic equilibrium is established in a closed system when the forward and the reverse reactions happen at the same time, at the same rate. Same time means simultaneously. Both the forward and the reverse reaction continue. They do not stop. Even though it looks for us on a macroscopic view as if it stopped, for us it will look as if nothing is changing, but on a microscopic level, there's definitely still a reaction where the particles are still moving forward, reverse, forward, reverse. Examples of dynamic equilibrium is chemical equilibrium, as we've done just now. We also have phase equilibrium. Think of something that's in a closed container that's allowed to evaporate, and then saturated solution and precipitate. We also have a dynamic equilibrium in that system. And that brings us to the end of this session. Have a good one. Welcome back to another session of Physical Sciences, specifically chemistry. I think when you see me, you know it's chemistry. So we're going to carry on with chemical equilibrium. The last time that we did chemical equilibrium, we looked at the definition of chemical equilibrium. We unpacked, we spoke a little about closed system, open system. We looked at reversible reactions, and We also looked at the definition of chemical equilibrium. We looked at the definition of dynamic equilibrium. And we looked at the graphs. On the graphs, we specifically looked at the rate graph, and I started to introduce the graph which we call the concentration graph. So what we want to do today is, we have now spoken about what chemical equilibrium is, what the features of a chemical equilibrium and dynamic equilibrium is. I want us to now embroid on it and go and look at what happened to the concentrations, the changes in the concentrations while we are doing these reactions, the forward reaction and the reverse reaction, and what is the constant. And we call this constant Kc, but it is actually called an equilibrium constant. So in this session, we will look at the equilibrium constant and what it is, and then in a later session, we will look at the calculations, how we calculate this equilibrium constant. In short, we call this equilibrium constant Kc. I used to say that it's a goal because of all this change, forward or reverse, becoming bigger or smaller. We call it Kc if we use the short name. The terminology that we need to think, and what I'm going to use now, is things like yield. Remember, yield is what gets formed when reactants react. We're going to look at, is it a lot that formed for the reactants, or is the yield less than the reactants, or what was put in? We're also going to look at this equilibrium constant expression, and we are going to look at this equilibrium constant value and how we work this value out. That brings us to the definition of equilibrium constant. As we said, Kc. Kc is the ratio of the concentration of the products compared to the concentration of the reactants in the equilibrium mixture. It must be at equilibrium, and this value holds for a specific temperature. This is very important for us to remember, and for a specific reaction. So what do we actually say there? Say, for instance, we have a reaction, and this reaction is happening at, let's say, 200 degrees Celsius, and we find out that Kc has a value for that specific reaction at 200 degrees Celsius. If we will change this temperature to 250 degrees or to 180 degrees, as soon as we change the temperature, your Kc value, this constant, equilibrium constant, will change. So it's very important to note at this point already that your equilibrium constant, your Kc, is sensitive to temperature. It only is affected by temperature. When we look at Kc expression, we use the concentration of the reactants and the concentration of the products. I just want to remind you again that concentration is the number of mole per unit volume. We use the square brackets for concentration, so this is the concentration of hydrogen. And when we work on the Kc expression, we only use aqueous solution and gaseous solutions. We do not use the liquids and the solids because liquids and solids have a constant concentration. We normally use a 1 to represent their concentration. The Kc value gives us an indication of the yield of a reaction. And because it is a ratio, it does not have any units. We have an example in front of us. We're quickly going to look at the production of ammonia again. Remember, I said that the reaction must be balanced. So when we use the balance reaction and do the ratio, or to do Kc, we always put the products on top and the reactants at the bottom. Now, firstly, you need to see that there's a coefficient of 3 there. There's a coefficient of 1 that we do not have to write, and we have a coefficient of 2. Now, when we do the concentrations of this in our Kc expression, we normally use the coefficients and it becomes a superscript. So we actually go work out, in this case we now have NH3, the concentration to the power 2. That comes from the coefficient. For hydrogen it's to the power 3 or to the exponent 3. So your coefficient becomes your exponent. As I said, we have for the ratio, remember this is a ratio, there's no units, we have the product concentration over the reactant concentration. For Kc, for us, because Kc gives us an idea of the yield, when Kc is bigger than 1, smaller than 1, then we always say there's more reactants than products. I always say then the denominator is big and the numerator is small. So we have this division and it will always have a number smaller than 1. When Kc have a value of bigger than 1, we know that we have more products than reactants, so we have a big numerator over a small denominator, actually ending in a number bigger than 1. Then again, I just want to stress that Kc value is only affected by temperature. Only when temperature changes, our Kc value will change. If we look at the last one, we have another example there of hydrogen peroxide that decomposes into water and oxygen. We now see we have a liquid there, and we know that a liquid has got no concentration, or we use a 1 there, and we do not include it in the Kc expression. So my Kc expression here will be the product concentration over my reactant concentration. I do not use the water because water here is a pure liquid. Remember that the coefficient becomes the exponent. And this brings us to what we call a break. Go and enjoy the break. See you soon. Welcome back after the break. I'm sure we're all refreshed and you took a sip on something that you enjoyed. Please hang in there with me. We will be going on. Before the break, we spoke about the Kc expression, and now I would like us to go and work with Kc calculations. Remember what I said? Kc stands for equilibrium constant, and the most important thing that you should remember is Kc is only affected by temperature. It must be like a rhyme for you. Kc is only affected by temperature. I would like us to look at the question. Ammonia is prepared, ammonia is NH3, is prepared according to the following balanced equation. Remember, I said it's important to know the balanced equation because we use the coefficients that becomes exponents in our Kc expression. At a low temperature, and this temperature is 350 Kelvin, an equilibrium mixture for the above exothermic reaction has the following concentrations. They tell us that at equilibrium we have the concentration of ammonium is 2 mole per decimeters cubed. The concentration of our nitrogen is 0.5 moles per decimeters cubed. And for the hydrogen gas it is 1,5 moles per decimeters cubed. I just want to refresh your memory again that concentration is equal to the number of moles per unit volume. We look at it. First thing that we need to do, like with any other calculation, we write down what was given. So we were given the concentrations of the nitrogen, ammonia, and the hydrogen gas. The very first thing, please make sure that you always, as soon as you have to calculate Kc, the first thing that you must do is to write down a Kc expression. For this one, remember, this is our products, and this hydrogen and nitrogen is our reactants. Okay. We were given the concentrations, and because we need to substitute the concentrations, we can substitute what was given to us. There is no need for us to convert it into a concentration or to find out what the volume is. Even if we don't know what the volume of this container is, we can still work out the Kc value. So when we substitute into the Kc expression, we will substitute the 2 there with the exponent 2. Then for nitrogen, we have 0,5 mole per decimeters cubed, and for hydrogen we have 1,5, and remember, for hydrogen this should actually be a 3, exponent 3 there. So, but if you work out this Kc, we have 2 exponent 2 divided by 0,5 times 1,5. Remember, 1,5 is exponent 3. That comes from the coefficient of our hydrogen. When we work this out, we get to an answer of 2,37. And what does that mean? You must always ask yourself, what does that mean for the yield of Kc? They also ask the question, what is the significance of Kc? When they ask you that question, they actually want you to talk in terms of Kc, is Kc bigger than 1 or is Kc smaller than 1? Now in this case where Kc is bigger than 1, I said to you it means that your products, which is your numerator, is bigger than your reactants, which is your denominator, and that leads to a bigger than 1 value. So what's the significance of Kc being 2,37? You will then say this means that the product is more than the reactants. Another question. Consider the following reaction. We have 2A, which is gas, 1B, which is also in gas phase, that converts into C, that is also in gas phase. What's important is, why do I talk about gas? Because as soon as I have to work out Kc, remember, Kc is working only with gases, and aqueous solutions. Kc, we do not use the L, which is liquid, and we do not use the S, which is solid. We take those concentrations to be 1 because those concentrations remain constant. They say to us further that we have 12 mole of A and 10 mole of B in a sealed container, and they give us the volume of this container. At equilibrium, there are 4 moles of our C and in our container, and the temperature that this happens at is 300 Kelvin. Why do they talk about the temperature there? Remember, Kc is only affected by temperature. So they need to tell us at what temperature this specific experiment is done. So the question then there is, work out or calculate Kc. Firstly, you write down what was given, and I want you to see that we have moles now. We don't have mole per decimeters cubed. So I want to remind you that C is equal to N over V. What they have now is they give us the number of moles of A, they give us the number of moles of B, that's in the beginning. Remember, your number of moles of A and B at the beginning is more, and it starts to become less as the reaction proceeds. But at the beginning, you need to remember that there is no C at the beginning. So the first thing, the most important thing that you must do is you need to write down the Casey expression. Write it down there. You can write it down again a bit later if you have to. Just remember, you lose your marks if you do not show the Casey expression. Then, because we're working with mole, we will now first have to go work out the concentration of A, B, and C. But this concentrations, we need to go work out what is the concentration of this at equilibrium. Now, we were told that the concentration, the number of moles here, is 4 moles at equilibrium. Right. When we work with this, we have what we call, teachers call it different things. I call it the rice table. Rice is as in rice that we eat. And I will explain to you now why I call it the rice table. The rice table is an ordered way to do the calculations. You can do it in any other way as long as you keep track of what you're doing. As long as you get to the end point, it's not really about the journey. But the journey that I would like to explain to you now is how to convert those moles into concentrations at equilibrium, and how to then use that concentrations at equilibrium to work out the equilibrium constant, or as we call it, the Kc. We call it the rice table. The rice comes from R, which stands for the ratio, and this ratio, as you can see, this ratio is actually the coefficient of your balanced equations. Okay, so we have a 2 for A, we have a 1 for B, and we have a 1 for C. I also want you to see that the next one, which is my I to make up rice table, is for the initial mole of my A, my B, and my C. The third row, we know that this little triangle that we call delta, we know that we also say that it means change in. So on this row, that little triangle means change in the number of moles. So change is a C, and that brings us to the next row, which is actually the equilibrium row. What is the number of mole at equilibrium? So we then take that number of mole that we will calculate there and convert it into a concentration by using C is equal to N over V. Where does V come from? V was given to us, and V is in the correct unit, decimeters cubed. Why do I say it's in the correct unit? Remember, when you work out the concentration, you need to have your volume in decimeters cubed, because your concentration unit is moles per decimeters cubed. Right, are we ready? What's very important is I want you to note this line here that's actually very bold. That very bold is actually an indication of whatever is on the left-hand side is my reactants, and whatever is on the right-hand side is my product. I want to focus your attention again that we only use gaseous solutions or aqueous solutions when we work out the Kc. We do not use liquids and solids. Back to what we're doing, I would like us to use another pen color. So what we should remember now is initially we had 12 moles of A, 10 moles of B, and we know in the initial states, and I just want to show you there, initially we have that number of moles for A and B, and we have no moles for our nitrogen. for C. So if I started off with 0 and I now have 4, it actually means I must have added 4 when I did the change. Where does that adding come from? Remember, in our forward reaction, our reactants start to convert into product. And as it converts into product, some of the reactants are now converting into the product. Therefore, we say plus. Then, this is a very important row because this row needs to be aligned with the ratio. So we can now say, to have the same ratio, we will say 4 times 1 divided by 1, which means there is 4 of my B. We can go work out in ratio how many moles of A must I have, which is 4 times 2 divided by 1, which is 8. But now we know that we actually used up our reactants, so we will put a negative there and we will subtract from there. Right. So if we look at the equilibrium constant and we look at our Rice table, we are now where we can say, I now have 12 minus 8, which is 4, and 10 minus 4, which is 6, and at equilibrium this was given. Now I know the number of moles at equilibrium, so I can go work out with C is equal to N over V. And we know V is 2, so it's 4 divided by 2, which is my volume, 6 divided by 2, and this is then my concentration at equilibrium. That brings us to the substitution of my concentrations into my expression, where I have C to the exponent of 1, A to the exponent of 2, B to the exponent of 1, and if we put them all in and substitute them correctly, we have a value of 0,17. What does that mean? When we have 0,17, it means Kc is smaller than 1. What does that mean? It basically means I have few products, but I have a lot of reactants. Right. To summarize, I just want to remind you that we spoke about a closed system. Chemical equilibrium only happens in a closed system, only reversible reactions. Your rate of your forward reaction must be equal to your rate of your reverse reaction, and the concentrations of everything remains constant. Then to summarize equilibrium constant or Kc, the ratio of your concentrations of your product and your reactants, it is expressed from the chemical equation. It only applies to a specific temperature. There's no units because it is a ratio. When Kc is bigger than 1, your products are more than your reactants. And when Kc is smaller than 1, your reactants are more than your product. Thank you very much for your time. We'll see each other soon.
Woza Matrix 2021 Catch-Up is brought to you by the Department of Basic Education, NECT, ETDP SETA, SABC, MultiChoice, and DBE TV on OpenView Channel 122 in partnership with